Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. Today we are very pleased to have Bernardino Romera Paredes, who is a researcher at Google DeepMind, where he has been a core team member of AlphaFold 2 for protein folding, Alpha Tensor for matrix multiplication algorithms. More recently, he has initiated the FunSearch, which is the topic of today, and which is a system using language models for program search, and has discovered a new mathematical model. Bernardino has an MSc in computational statistics and machine learning from UCL in London, where he did also his PhD studies, and that included an internship at Microsoft Search. After finishing his PhD studies in 2014, he joined the Tor Vision Group as a postdoc at the University of Oxford, and nowadays, as I mentioned, he's at Google DeepMind. He has several papers published in Nature, as well in top machine learning conferences such as ICML and NeurIPS. We are extremely pleased of having you today here, Bernardino. For the audience, please remember that Bernardino is happy to take questions, so just put them in the chat and I will read them for him. And otherwise, at the end of the presentation, we will have the usual Q&A session. The floor is yours, Bernardino.
Great. Yeah, thanks a lot, Dolores. Thanks a lot for inviting me, for having me here. And thanks, everyone. So yeah, today I'm going to talk about our last project, about FunSearch. And just before getting into that, I'd like to give a bit of context about what this project, or where this project is coming from. So within Google DeepMind, I'm part of a team that is called the Computer Science Team. And the aim there, the goal, the motto is to apply artificial intelligence in order to discover new and verifiably correct algorithms that are able to outperform the state of the art in impactful problems. And within that, yeah, we're interested in anything that can be framed into this statement. And our first project came in the fall of 2022, and it was called Alpha Tensor. And the point of this project was to use reinforcement learning to come up with new and better algorithms for matrix multiplication. So better as in with better complexity. And in fact, we were able to find better algorithms for some specific sizes of matrices. And that was really, to me, that was a pretty good project. Also, I learned a lot, and yeah, and the results, we didn't know whether they existed before we started, and it turns out that they do, and it's great to use machine learning or AI to find those. But one kind of limitation about this was that the kind of essentially we were searching in a constrained space of algorithms. So we were searching for algorithms which had a very specific form, which is a set of sums followed by a set of multiplications followed by another set of sums. Now this is great for matrix multiplication, but for many tasks out there, this is quite constraining. And back then we were kind of fantasizing, like, wouldn't it be amazing to actually be able to search in the space of general code? And yeah, that could be really cool, because that could allow us to do many more things. So in particular, why searching the program space or the function space is good, or it's interesting? Well, it gives us several nice properties. So first of all, it gives us generality. So we don't need to specify any structure in the solution, unlike before. And also gives us a universal interface, because anything that can be anything whose solution could be expressed as a program is something that we could then attack. Another point is that of interpretability. So given that what we would get as an output is a piece of code, we can look at that code, we can try to understand that code, we can tinker with the code. So it's it's easier for us. And also it gives us scalability, because given that code is a concise representation, it tends to scale to much larger instances of a problem as opposed to traditional search. So now the key piece, the key component that allows us to explore, to search in the space of code is, as you might be thinking, is large language models, these LLMs. So we bring this component, and then essentially we created what we have called FunSearch, and we published all the experiments and the description of this method in this paper that appeared in Nature at the end of last year. So to start talking a bit about that, as I mentioned, LLMs are the key, a key part of this. But LLMs on their own are not enough. So can LLMs find and code algorithms? So the answer, in principle, is for simple problems, definitely, it can do a pretty good job. And probably all of you have been thinking with that, and they are getting even better. However, as I mentioned before, the kinds of problems that we're interested in here, they are about open problems, about finding new things, about finding better constructions, about solving open questions. And for those kind of problems, LLMs are not there. They are not enough. You can ask these kind of questions, but all the LLM can do is at best find some or produce some modification of some code out there. Is definitely not what we are after. So in this project, what we focus on is on problems that admit a fast evaluator. That is, it's easy, or we can have a function that computationally tells us whether a solution is correct or not, and also how good this solution is. So we focus on these problems, and also problems that are hard. So hard, but also have a fast evaluator. And it turns out that out there are many such problems. So this can be applied to in principle to many of those. So just to clarify this, so the input to FunSearch, I will go about that. I will go deeper a bit more about that, but just for now, it's easy to think of this as the input of FunSearch is just a function that evaluates a solution, and then the output of FunSearch will be that solution in the form of code. So I'm going to start talking a bit about results before talking about how it works. And I'm going to talk about the main results we report in the paper. So the first set of results is about the largest independent set. This is a theoretical problem that is about finding the largest independent set in a graph, and that's known to be an NP-hard problem. So here, in particular, we focus on the CAP set. So it's a specific family of graphs called the CAP set graphs, which have a high mathematical significance. For example, mathematician Terry Tao is pretty fond of this problem. And as it turns out, FunSearch is able to find constructions that improve over the state of the art in this problem. So just to give a bit of intuition about what this problem is about, we can look at this thing here. So first of all, I should say that there is an instance of the CAP set problem for every number of dimensions. And the question here is to find the largest possible set of vectors or set of elements in F3 to the n, such that no three of those lie on a line. So for a given number of dimension, we have 3 to the n elements. So it's useful to focus here for illustration purposes on 2 dimensions. So in that case, we have 9 elements that are the ones you see here in the right. And then the point is to find the biggest subset of those elements such that no 3 of them lie on the same line. So we can start with one element, another element, we got another element, but then we say, okay, hold on, there is 3 elements now in the same line, so we cannot add this last element. So then we remove it. Then we add another element, property still holds true, and there's another element. And then we have found a CAP set of 4 elements for 2 dimensions. Now, it turns out that indeed, for 2 dimensions, the best you can do is to find a capset of 4 elements. And yeah, no matter how you try, you cannot do better. And that's not too difficult to see. But as the number of dimensions increases, things get really hard. Like the problem becomes difficult to deal with. So capset is one instance of the problem of the set of problems I was mentioning before, because it has an evaluation procedure that is efficient. So first of all, we can verify whether a capset is correct or not by just checking this property I mentioned before about no more than 2 points in a line. And also, it is easy to measure how good a capset is. We just need to count the number of elements that we have added to the capset. So we have applied the FunSearch, given that this problem is quite feasible to apply FunSearch to, and then we apply that on different dimensions. So for small dimensions, FunSearch was easily able to find solutions, constructions that match the state of the art. So for 1 dimension, you have 2, 2 dimensions, you have 4, as we've seen. For 3 dimensions, you have 9, and so on. Now, it is known that up to 6 dimensions, we know exactly the size of the best capset possible. But beyond 6, it's still an open problem. So for n equals 7, FunSearch was able to find a similar construction, or a construction with the same size. And then for n equals 8, it turns out that FunSearch was able to surpass the state of the art, going from 496 nodes to 512. And that was pretty great. Also, by using a different kind of construction that mathematicians have been developing, that is called the admissible set, we apply FunSearch there, and then by using that, we were able to improve also the asymptotic result. That is how the size of the capset evolves as the number of dimensions tend to infinity. So we were able to improve that bound as well. And these are great results because, as far as we know, this is the first time that new results that improve over the state of the art have been obtained by leveraging LLMs. On top of these results, we have also applied FunSearch to other problems in maths, in particular the Shannon capacity over cycle graphs and also the corner problem. And we talk about them in the appendix in the paper as well. So even, let's say, just as important as finding new constructions is also the way FunSearch produces those constructions. So in a normal search procedure, in a traditional search method, the output that you would get would look something like the thing you see here in the left. So it's essentially a raw list of vectors, one after the other. So it's nice to see the output, but it's difficult to get anything out of that. On the other hand, FunSearch produces a piece of code that is easier to get some story. It's easier to get something from this. Like it's easy to see what it is doing and how it is constructing the final list of vectors. And this is not just a hypothetical thing that I'm saying. Like code is simpler. It is simpler, but it is true that sometimes it can be well, difficult to understand. But it turns out that the code that FunSearch produces is actually interpretable in many cases. And in fact, Professor Jordan Ellenberg, we've been collaborating with this professor, and he's, among other things, a co-author of a breakthrough in the capset problem in the last 5 years. When he saw some of the programs that we supplied, he said that the problem supplied by the LLM is far conceptually richer than a mere list of vectors. I am learning something, which is really great to see, because I mean, he knows a lot about this problem. And just to bring this point home and to emphasize how important this is, I'm going to show here another example of how this also plays, or how the fact that we can talk, we can communicate through code can be important. So in this case, the code you see on the left is code produced by FunSearch on the admissible sets problem, which is as I mentioned before, is the capture problem when considering the asymptotic case as n tends to infinity. So this piece of code here was able to improve over the state of the art by a bit. And then what we did was to look at this code, and then we realized ourselves, humans, we realized that this code has some regularities. In particular, that this function treats tables of coordinates together. So it treats triplets in the same way. So then we wondered that maybe this function is exploiting some kind of symmetry about the problem, some symmetry that we don't know that it exists, but maybe it does, and then it is exploiting that. Now, we don't know whether this symmetry is there or not, but what we did is assuming that this symmetry existed, and then we re-encoded the problem, but assuming that this symmetry was there, so that the search can be restricted to symmetric solutions. Now we took this new specification and put it back into FunSearch and ran FunSearch again, and then we were able to get even better solutions. So we were able to improve the state of the art even beyond what we had before. And that's really great because, as I was saying, by means of code we can kind of interact. So we can collaborate in a way like humans and the system. Now, another question which I found a bit intriguing is why is searching in the function space working so well? And to be honest, we can only hypothesize. I don't know, right? But we do have I think an interesting hypothesis, which is that many problems or most problems that we care about have some kind of structure. They are structured in some way, and as a consequence, many of the solutions might have also some structure. And some structure in the sense that they have small cosmograph complexity. So the cosmograph complexity of something, say, for example, of a string, is the length of the shortest computer program that produces that string. So, for example, the cosmograph complexity of AB is way smaller than the cosmograph complexity of a seemingly random sequence, because you can easily find a small program that produces the first one. So what we believe FunSearch is implicitly doing is it has an implicit prior that encourages simple solutions, simple in the sense of that they have a small cosmograph complexity. And by having this implicit bias, that's beneficial because solutions to those problems with structure are easier to find. Okay, so this is the first kind of set of problems that we've been working on, which have more like a theoretical flavor. And the second problem we focus on is more practical. It has definitely some real world impact. So the problem is online bin packing. So bin packing is about finding the most resource efficient way to pack items of different sizes onto bins. And now the online version is the same, but in this case, we get items one at a time. And each time we get an item, we have to decide in which bin we put it. So we have to create a strategy such that we define into which bin each item goes. Now, online bin packing, it sits at the core of many real-world problems, from loading containers with items of different sizes to allocating compute jobs in data centers. And the overall objective is, of course, to minimize costs. So as you see, it's many real-world cases are in a way are online bin packing in disguise. So what we found here is that by using FunSearch, it is able to find solutions that are automatically that are tailored and outperform established heuristics. So here, here you can see an example of an instance of online bin packing where the blue rectangles are items, and each square, each rectangle is a bin. And here we compare best fit, which is a standard heuristic in online bin packing that puts each item into the bin where it fits the tightest. We compare that to a function produced by FunSearch. So here you can see that best fit required 52 bins, whereas FunSearch only required 50. Now, this is just an example, but it tells you a bit about how it does things. So in order to look a bit into what FunSearch does, we can have a look at one of the functions that it produces. So first of all, this function takes as an input an item, which is the input, the item that comes next. In particular, what it has is the item is the scalar corresponding to its size. And then the second argument is bins, which is a list or an array of bins, and in particular is the remaining capacity of the bins where the item can be put into. Now, the output of this function is also an array of the same size as bins, and the number on each of the elements in this array, it tells you the score. So essentially, we run this function heuristic, and then we will get a vector of scores for each of the bins, and then we will choose the one with the highest score. So the task for FunSearch is to produce a score for each of the possible bins. Now, I'm going to go through the function, but before I should say that FunSearch, or the LLMs that we use in FunSearch, they produce code together with comments. But in this case, the comments that we have here are not produced by the LLM. They are we wrote them to make it clear to ourselves what the code is doing. So let's have a look at what the function is doing. So first of all, it creates score, which is an array of the same size as bins, which is nice because that's the size of the output, and it initializes that with a value of 1000 for all bins. Then it penalizes bins with large capacities, which makes sense, and then it extracts the index of the bin with the best fit. And just after that, it gives it a bonus, so it scales it with the size of the item, but then it penalizes it if the fit is not tight. So if there is a big gap once you put the item into the bin, then this will be highly penalized. And that makes kind of a lot of sense because if after you add the item into the bin, if there is a small gap, then this small gap is going to be difficult to be filled later by subsequent items. And as you can see in the image above, in the example, you see that most bins in FunSearch are tightly filled, as you would expect, using this heuristic, and that turns out to be pretty important. So, of course, this is the example above is just an anecdotal example, and of course we have tested this across many data sets, and in all cases we have found that FunSearch is able to lead to better results, and in some cases much better results than the competitor heuristics. Now, when it comes to thinking about procedures to automatically tailor let's say heuristic, ways to automatically find strategies to deal with a problem, it's normal to think about neural networks and things like that, reinforcement learning and so on. But FunSearch has some advantages over this. FunSearch can also be used to automatically produce programs and strategies that are adapted to a specific use case. And unlike neural networks, and unlike these kind of approaches, the output of FunSearch is code, and that's pretty interesting because it gives us many advantages. In particular, it is easier to deploy because in this case we don't need specialized hardware, like for example GPUs or TPUs. It is also easier to debug because, well, it's not as much of a black box as a neural network is. As a consequence, it's more understandable and more predictable, and it is also more reliable. So I hope that by now, after these two main examples of capset and online bin packing, you can get a broad sense about what FunSearch is capable of. So in the rest of this talk, in this presentation, I'm going to talk a bit more about how FunSearch works. So as I mentioned at the beginning, LLMs by themselves, they cannot solve, or they cannot come up with novel solutions to problems. They often come up with plausible solutions, but they are often wrong, which is, well, it's often referred to as hallucinations. But the good thing here is that we can couple LLMs with, say, Python runtime or any other runtime to provide grounding, to provide the ground truth here. And we can use both, and then you can search in that space of code, and we do this search by using evolutionary algorithms. So just to give a bit more of intuition before explaining a bit more, it's pretty useful to look at this score map of functions here. So in this score map, every point there represents a function in Python. So the blue regions of the space represent functions that are not too interesting, whereas the red ones represent functions that are interesting, that found good solutions. So initially we start with a trivial function, usually, like the one you see here in the right, solve is 0. Now, one thing we can do is to create a prompt out of this by adding a new header, a new function header called solve_1. And then we ask the LLM to implement the body of this function. Now we can use this prompt, we can introduce this prompt into the LLM, and then we can sample new functions. And we can sample this many times, but by doing so, it is unlikely that we get to regions of the space that are interesting. But instead, what we would get is probably functions that are in the neighborhood of solve 0. So instead, what we can do is to chain mutations. And by chaining mutations, I mean that you take the best functions that have been generated, and we can tell which functions are better than others because we have this evaluation procedure that I mentioned before. So we take the best functions and then we create new prompts that use the new best functions. So we can iterate this procedure over and over, and then by doing so, we will get closer and closer to the most interesting regions of the space. Right, so just to be a bit more specific, this is a bit how FunSearch works. So first of all, we start with a specification, an input specification about the problem we want to solve. And this specification is nothing else than essentially a seed function that we want to evolve. As I mentioned before, we usually start with something very simple, and then a function to evaluate those solutions. Now, we take the function, the initial function to evolve, the seed function, and we put it in the program's database to initialize the program's database. Now, at every point, at every moment in time, what we do is we sample two functions from the program database, and then we create a prompt using those functions. Like in the same way as before, we put these two functions, and then we create a header of yet another function, and then we leave it for the LLM to complete. So we use this prompt as an input to the LLM, which is a pre-trained LLM, and we sampled several times. We will get several new functions, and then we will evaluate those functions. So it may be some functions lead to not correct outputs, but some of them will, and then we will score those, and then for the functions that have interesting good scores, then we will put them back into the program's database. So now we keep iterating this over and over, and then at any point in time, we are free to query the system to tell us what the best program or the best set of programs have been found. So we can check, we can monitorize how much progress we've been making. Oops. Yeah. Now, regarding the programs database, one key thing there is about keeping diversity, and it is a key component to keep to maintain some level of diversity among the functions, because otherwise we could get stuck into small region of the space, and essentially we would be stuck into some kind of a local optima. So in order to maintain diversity, what we do is to use islands, which is a very well-known technique within the generic algorithm community. So essentially, instead of evolving just a single population of functions, what we do is we evolve several populations that we call, or people call islands. In this figure, I show 4 of them, but in a normal experiment, we usually have 10. And what we do is, we evolve them separately, but then every 4 hours, we automatically spot some of the worst islands, and then we kill them, we erase them, and in their place, we put one of the best implementations found, one of the best functions found from the other islands as a new seed to start these new islands yet again. And then evolve separately again, and then we keep iterating this procedure over and over. And one way to think about that is that we keep in parallel several experiments. We keep them running, and then every now and then we spot the ones that are not too promising, and then we just cancel them, and in their place we just start a new experiment with a good function that have been found by the other experiments that are running in parallel. And this is of course done all automatically, so we are not involved in the process. And as we will see, this simple procedure turns out to be important for keeping diversity. Okay, so some other components that are also worth mentioning. So first of all, we use pre-trained LLMs. So we just take LLMs that have been pre-trained before. We don't do any training at all. We don't throw any gradients. We just take LLMs that have been pre-trained. And also, another important thing about LLMs is that ideally, we would like to use LLMs that are as fast as possible, because we would like to explore the space of functions as much as possible, and as a consequence, the faster the better. But also, we would like the LLMs to be as powerful as possible. And usually, as we have seen, the bigger they are in terms of parameters, the better. However, these two elements, these two properties are in tension, right? So the more powerful an LLM is, usually the slower it is in terms of inference. So we have to arrive at a trade-off, and for all the experiments we had here, we've been using Cody from the Palm 2 family in Google. Now, another key point about FunSearch is that it is implemented as a distributed system. So before, when I showed the previous diagram of FunSearch, I described it as a sequential or iterative kind of procedure. But in practice, it is implemented as a distributed system in a way in which there are many nodes that talk to each other in an asynchronous way. In particular, in a standard experiment, we use 15 samplers, 15 LLM samplers that produce functions and keep sending those functions to in the order of hundreds evaluators, and all these nodes are connected to a central program database, which keeps the functions that have been found so far, as I've mentioned before. And this is also a key component for FunSearch to work well. Finally, another very important component is the skeleton. So here by skeleton, I mean the set of code that you can specify beforehand in a problem. For example, including boilerplate code, but also well-known algorithms or structure of algorithms within the context of the problem you are dealing with, so that you leave to FunSearch to implement the key part of the algorithm that governs the logic of the whole algorithm as a whole, the whole behavior of the algorithm. So, for example, if you want to find a strategy to explore a big graph, you can leave to FunSearch to evolve a function that decides which node to explore next. At the end of the day, the key point here is that we cannot cheat, right? So we are what we are after in our project, by using FunSearch, is to come up with new things, with new kind of functions, with new kind of algorithms, and to come up with new ways, or to come up with new solutions to open problems. So if you are able to improve the state of the art, we are quite sure that the function that FunSearch has produced was not in the training set. So essentially, we can throw whatever we want. Essentially, we can throw anything in the skeleton, because our objective is to actually find something new and something novel and useful. So we have done quite a few ablation experiments that we describe in the appendix of the paper, and here I'm going to mention 2 of those. So the first one is about assessing the impact of the LLM used. So in this case, we compare Cody, which is the model that we've been using for all the experiments, with StarCoder, which is an open source LLM that has been trained mostly on code, and also random. So here, a random baseline corresponds to using no LLM, and instead is used our own implementation of genetic programming. So here we see that Cody and StarCoder actually do pretty well. So Cody is able to find the best solution in this example, but StarCoder is not. It's actually comparable. Like if you see, it has lower variance. StarCoder is able to find better, like good solutions in all of the runs. So essentially, using one or the other doesn't lead to huge differences. On the other hand, not using an LLM is definitely, there is a big gap. We let the baseline random version of this run for way longer than what is being shown here, but it wasn't able to get any close to when using LLMs. Now, for the second ablation experiment, what we did is to take FunSearch as it is, and then each time removing one of the properties of FunSearch. So FunSearch as a whole is the blue line that we see it performs the best. And then the next line, which is the green one, is about without merging. So here, what we, well, as I mentioned before, when we build a prompt, we take two functions from the programs database. And the reason for us to do this was that we were thinking that by providing two functions, maybe the LLM was able to somehow combine these functions in some way. But here in the green line, we test using FunSearch with only one function. So we only create prompts by sampling just one function. And as you can see, results are not too different. So essentially, the green line is slightly worse than the blue one, but it's not significantly worse. Now the next line, which is kind of yellow, is about less diversity. So here, this line is about using or not using islands. Essentially, the yellow line is essentially not using islands, or in other words, just using one island. And as you can see here, that does have a significant impact. So we do benefit significantly by actually using islands. Now the next line is the pink one, which is about using skeletons or not using skeletons in this case. So we can see that not using skeleton in this case, it has a big significant effect. And finally, the last one is without evolution. So that is you take FunSearch, but then you just keep sampling from the initial prompt over and over from the initial function. And of course, in this case, you can see that the results are really bad. Okay, so which problems is FunSearch useful for? So we have found three properties that can tell us a lot about whether a problem can be solved or can be expected to be solved by FunSearch or not. So first of all, it is required that we have an efficient evaluator. And by that, I mean an evaluator that is able to provide a score in a matter of minutes or less, and using a decent amount of memory, but not too much. The second point is about having a smooth scoring feedback. So that it is possible to gradually improve the solution. So it is easy to tell among two solutions which one is better than the other. So it is easy to spot good stepping stones so that we can build on top of those stepping stones in order to get to new ones down the line. An example where this doesn't hold true, just to give you a bit of an intuition, is on theorem proving, for example. So in theorem proving, you want to, at the end of the day, you get feedback about whether you find a proof for that theorem or you don't. So it's either 0 or 1. So this is not a kind of problem where FunSearch can shine. And finally, it is nice, it's desirable to have prior information about the problem, because that would allow us to build a good skeleton. So finally, to conclude, I would like to emphasize that this is just the beginning. So in this work, we have striven for simplicity. So all the decisions we've made along the way, essentially we have first tried the simplest thing that we thought of. And in many of those decisions, it turns out that it worked pretty well. So we kept those. And that's really great, because that creates a strong baseline, but also it creates a base from which we can now build on top of it. Now, another thing I would like to say is that as you've seen, we can take any LLM here and essentially plug and play. And as LLMs are getting, as we can see, more powerful, but also cheaper to run and faster, that altogether make us very confident about the groundbreaking potential of FunSearch. So finally, I would like to thank you a lot to every member of the team. It's really an amazing team. And of course, thank you all for your attention, and I'll be happy to answer any questions you may have. Thank you.
Thank you, Bernardino, very much for your great presentation. So to the audience, if you have any questions, please raise your hand and we will give you the rights to the microphone and the camera. I guess you make the presentation crystal clear. Yes, so Marco, Nuria will give you the rights.
I think you can hear me?
Yes,
yeah.
Okay, so first of all, thank you very much for the presentation. It was really interesting. I was wondering, how often, like, once you start the, say, experimentation, how much do you have to intervene in the, let's say, while it runs, and how much it's completely automatic? Do you have to stay after the LLM like constantly, or you can keep it going for a while and then just check it every now and then? I don't know if it makes sense or if it's clear.
Yeah. Oh, thank you for the question. Yeah, totally. Yeah, thank you, Marco. Yes. Yeah. No, it's an interesting question. So definitely, we don't need to stay all the time looking at the LLM for sure. So what we do in practice is we start defining a specification of the problem as an input, and then we run FunSearch, and every now and then we look at the best functions. And sometimes by looking at those functions, you can spot you can realize, okay, I made that mistake in the specification because the system is exploiting something that I didn't consider, so I need to go back and then re-implement or change a bit of implementation so that FunSearch cannot exploit this bug that I introduced. So these are the kind of things that are end up being quite common in experimenting with FunSearch. Another thing is about defining the input of FunSearch, this specification. So that's also, there are a lot of things to do there. Like you could, as I mentioned before, the skeleton is kind of an important part. So given a problem, there are different ways of approaching it. So you can try also to try different ways of defining the input, on defining the skeleton, and then you can launch several experiments maybe with different ways to approach the same problem. But once you launch an experiment, no, you don't need to monitor it much. Like it's nice to see every now and then, like the curves where it has found some new solution that improves over the previous ones, and how fast it gets there. And then you can look at the actual functions, and then you can learn from those functions. But it's not that it requires a lot of babysitting. No, I wouldn't say that that's the case.
Okay, thank you very much.
Thank you.
Thank you very much for the question. Are there any other questions from the audience? Okay, Francesco. So Nuria will give you the rights. I think you can speak now, Francesco.
Hi, do you hear me?
Yes.
Okay. Hi, thanks for the presentation. My question is simple, I think. How many hardware resources were needed to achieve those results?
How many what? Sorry?
How many
Resources?
computational power? How many?
Yes, no, that's a great question. Yeah, so we do provide some section on this in the appendix. I don't remember the exact details, but every experiment is not okay. Let me say it. Every experiment is around $500 worth, or like yeah, it takes around $500 to run. Now, for some cases, you run one experiment and then you get already pretty good solutions. Like this is the case, for example, with admissible sets and online bin packing. For others, you do need to run many more experiments. Like for example, for the cap set finite version, for that you need to run more experiments. So yeah, it depends a lot on that, on the hardness of the problem. But just running one experiment is around 500. So essentially, you need around 15 samplers for over a day or a few more days, and then around hundreds of CPUs to evaluate those programs.
Okay, thank you.
Thank you, Francesco, for the question. Mehdi, do you have a question?
Yes. Thank you for your presentation. I have one question. When you're generating these functions with LLM, what do you change in iteration so the LLM can generate a new and different function from the previous one?
Mm-hmm. Right. Yeah. So the prompt that gets into the LLM, it takes in a normal iteration, it takes two functions that have been sampled from the prompt from the programs database. So we keep a programs database, so with all the functions that have been generated so far, and then at any point, whenever we generate a new prompt, we sample two functions from this database. So in this sense, every time we will get quite likely a different kind of prompt. Now, on top of that, there is the inner stochasticity of the LLM. So even with the same input, you might expect you might get different outputs. You also have that. And one more thing I should say is that I didn't mention about the specificities of sampling from the program's database, but one thing I should say is that we score the functions. So each function receives a score, and we sample functions that have higher scores. We sample them with higher likelihood. So of course you also have that. But yeah, essentially, yeah, there is a lot of stochasticity in the process, and that's why the LLM sees many different functions, and it keeps producing again a high variety of functions.
Thank you.
Thank you very much, Mehdi. Are there any other questions from the audience? I think there are no more questions for the time being. So I would like to thank you again very much, Bernardino, for coming today to the online seminar series, Machine Learning Needs Mathematical Optimization. So we are taking 2 weeks off, and we will be back the second week of April with more talks. And please to follow us. Remember that we will, you can use our QR code or our website, which is there in the poster of our online seminar series. So thank you very much to the speaker again, and thank you very much to the audience for joining today.
Thank you, Dolores, and thank you, everyone. Thank you.
Thank you to you, for making this.